Covalent bonding is more complicated. Covalent bonding is a situation where if I have two elements, to avoid a charge imbalance, they might come together and share electrons in order to make their noble gas configuration. So if we look at hydrogen, we think about giving hydrogen the same number of electrons as a noble gas, that would be 2. But that would create a negative charge, which normally a -1 isn't that great. The halogens do it readily, no problem. But for hydrogen, because that's 2 negatives and only 1 positive, that creates a 2-to-1 ratio, which is very imbalanced. Right? That would be the equivalent of like maybe an atom with 30 protons having 60 electrons. 2-to-1 negative to positive ratio, it's not balanced at all. Right? It needs to be balanced. So what we need to balance out this negative charge here is another positive charge. So the positive charge just is another hydrogen without any electrons. And so the hydrogens share the electrons. So each hydrogen still only has really the 1 electron it came in with, which is not enough to make a noble gas configuration. But when they share, the 2 electrons surround both nuclei, and both nuclei have 2 valence electrons, which is the same number as the noble gas configuration. That's the key here. You want to have a mental picture of what these electrons are doing moving forward, and that'll be really helpful, especially if you go on to take organic chemistry. So let's look at a couple of these simulations and try to develop our mental picture of what's happening here. So this one, maybe cover this one first. I like this one because it helps you to think of the electrons as a cloud. And so the Lewis structures, the one you guys drew for the quiz, and the ones that we'll be drawing, we think of the electrons as dots, right? We draw them in as dots around an atom or as a line between 2 atoms, which represents 2 dots that are shared between the atoms. But that's really not what they are, right? We know they're not really particles. In an atom, they behave more like waves. And so we think of them as being in an orbital, and the orbital represents where the greatest electron density is, and that's kind of like surrounding the nucleus in this 3-dimensional shape. It could be spherical like an s orbital, or it could be more elongated like a p orbital, something like that. So that's, when you think about what the molecule actually looks like, you want to think about the orbitals. You want to think about the electron cloud, the electron density being able to move around the atom. And it's not like a particle, and it's not stationary. It has the ability to shift around. So if I have an atom and I move its positive charge a little bit, then the electrons move around that, right? Because they're negative and they're attracted to it. And they kind of have the ability to flow. So I like this one because it allows me to see if I move the positive charge, the electrons will just flow back into an optimal distance from that positive charge to make attractions to it. That one's pretty straightforward. So this one is also really nice. It shows what happens to the electrons when atoms get close enough together. So you guys can see I've got a positive here and a positive here. So this would be like 2 hydrogen atoms. So right now, they're at a pretty far distance. But they are still just close enough for this outer area of energy density of one atom to kind of combine with the other atom's area of electron density. If I said energy density, I was a mistake. I meant to say electron density. But for the most part, the electrons are either here around this nucleus or here around this nucleus. Right? So this is not really a covalent bond yet. If I have a covalent bond and I stretch it to its limit before it breaks, then it might look something more like this. So if I want to bring it into the correct distance between the nuclei and pull the nuclei together, now I have something that looks a lot more like a covalent bond. So this is when you draw on paper a Lewis structure and you have a line between 2 symbols, a line between 2 atoms representing a covalent bond. This is really what it looks like. You have the 2 nuclei, and they've gotten close enough where their outer energy level of electrons is starting to overlap with the outer energy level of electrons from the neighboring atom. And when those orbitals from one atom overlaps with an orbital of another atom, when they get close enough to overlap, then I get a great feel of electron density between the atoms. And that's probably still slightly stretched from its optimal distance. If I pull them closer together, that might be more like the optimal distance. And when I have the atoms in a covalent bond, what I see is the electrons are no longer in atomic orbitals. If I have a single hydrogen atom in the ground state, where's the electron in a single hydrogen atom? It's in the 1s, right? That's a spherically shaped orbital. When that hydrogen gets close enough to the neighboring hydrogen for its 1s to really overlap with the other hydrogen's 1s, the 1s's combine together. Right? What happens if two waves crash together? They might cancel each other out, or they might add. And that's what happens because the electron orbitals are waves. They don't exist in the same way they existed before, though. So I don't have the 1s here and the 1s here. I have a new orbital that extends over both atoms. That's the advantage to forming a covalent bond. Because when the electrons get in this new orbital, that's two electrons. So there's two electrons moving around everywhere in this area of electron density, and as they're anywhere in there and everywhere in there at the same time, they are able to satisfy both atoms' noble gas configuration. Two electrons is what each atom needs to make the same number as a noble gas, helium. And that's what they both feel like they have because they have those two electrons surrounding both nuclei. It's also stable in terms of the charge attractions because you might say, well, if I bring these positives together, they're going to start to repel. That's true if I bring them too close together. But with the electrons spending the majority of their electron density in the middle of there, that actually forms negatives between the positives, which creates more attraction. So that is what you want to think about when you think about a covalent bond. So the rest we'll save for later in that simulation. So this simulation shows the energy difference. So for neon, there's not much energy difference because neon doesn't really form bonds very easily. So let's go to oxygen and oxygen. So what do we see here? So I'm going to pull this other. So I've got two oxygen atoms. You might not be able to see those because it's kind of bright here, but I've got one here and one here. I'm dimming the lights more. Okay, they made the oxygens orange. I don't know why. But what are the oxygens? They're not like hard spheres, right? They're just showing the outer electron cloud, the density of the electrons in the outer energy level. So when I pull the oxygens apart to the point where their orbitals can't overlap because they're not close enough together, I don't have a covalent bond yet. Right? So there's no really potential energy is like zero there. There's no energy or stability associated with that bond because the bond isn't formed. And so if I bring this oxygen closer until its orbital starts to overlap with the other orbital, now the energy goes down. Why does the potential energy go down once I start to bring the atoms close enough to significantly overlap? Right, I've got electrons now. So before the oxygens get together, neither atom has enough electrons to complete its second energy level and make the same number as a noble gas, so they're not very stable. When I bring them together, each oxygen's electrons that are now shared between them can satisfy both oxygen's octet or noble gas configuration. Plus, when I bring them together, what we said before, this simulation doesn't really show it as well as the last one did, but there's an optimal distance. If I put them right at that optimal distance, those electrons, and you can't even really, I wish they would show where the nuclei are, but they're here. The nuclei are quite close together, but the electron density between the nuclei that's where the electron density is greatest, and that forms the negative charge attractions to pull the positive charges together. So there's an optimal distance to maximize the number of attractions. If I push them closer together, then the energy shoots way up really fast. Why is that?
Because the force going higher up? No.
So it has to do with the attractions and repulsions, right? So this is potential energy, more attractions, more stable, lower in potential energy, less attractions or more repulsions, unstable, higher in potential energy. Right? So when there's no attraction, I'm like at the baseline. When I start to form attractions, it goes down and energy becomes more stable. And then I hit the minimum, which is the optimal distance for that bond. Then, if I push the protons closer together, then I do really get serious repulsion between the two nuclei of the proton. If I push them so close together, there's not really much space between them for electrons to attract them together anymore. Now I just have the areas of positive charge getting too close. That causes a lot of repulsion. And so that repulsion causes the energy to go way up really fast. So it's a balance between attractions and repulsions. So that's why we have covalent bonds, because there's an optimal distance. One thing I do like about this is it shows that there's a vibration involved in that bond. And so if I pull this atom apart, it's too far away to attract. But once I get it close enough to attract a little bit, the attractions pull together. And it will vibrate. At room temperature, things will be colliding with this, and the bond might stretch even more and then vibrate back down to its normal distance a little bit. So that kind of shows you, it gives you another idea of what type of mental picture to make for a covalent bond.